general relativity step by step. Last time I was talking about the 4 velocity and I came out with this rather beautiful formula here, and I was making the observation that the 4 velocity, certainly in contravariant components, for low speeds has got the 3 velocity UVW with a 1 there in the time position. Quite a nice indication that the 4 velocity is a meaningful concept. What I'm going to do now is to consider what happens when I transform my coordinate frame. So I'm going to set up x and t coordinates. There am I'm sitting here, and I've got an object that's moving by like that with a 4 velocity of u. And of course u is just going to be equal to gamma, gamma u, gamma v and gamma w, where gamma equals 1 over root 1 minus beta squared, and beta equals the modulus of u as a 3 vector divided by the speed of light. Well, that's great. I can do that, but what happens to my friend Baz in his spaceship? And here he is. There's a little spaceship, and Baz is sitting in there. Baz, give him a bit of livery. He's sitting on there and he's moving at speed. I don't have any letters left for speed. I'm going to call it speed alpha. No, I can't even use. Oops, I can't even use Greek letters. Speed A, B, C, D, E, F, F. Speed F. Let's try speed F in the x direction. So there he is. And what I want to know is, how does Baz, who of course has barred coordinates system, x bar 0, x bar 1, x bar 2, x bar 3, how does Baz perceive this situation? What are the components of the 4 velocity for Baz? Well, I'm just going to call it u bar 0, u bar 1, u bar 2, u bar 3, and that equals, by construction, a linear function of the 4 velocity as seen in my reference frame. W multiplied by a matrix which corresponds to the partial differentials bar I and j, which relate my coordinate system to his coordinate system. And of course that's just a Lorentz transformation. So let's just say he's going with speed vf. So I'm going to define beta, what shall I call this? Beta, can't call it bar, beta b for Baz, equals f, because that's his speed, divided by the speed of light, and gamma b is going to be equal to 1 over root 1 minus beta b squared. So that's his Lorentz transformation. So I can just draw it in. Gamma b, beta b, 0, 0, gamma b, beta b, gamma b, 0, 0, zeros here, and 1's off the diagonal. 1's on the diagonal, I'm sorry. And so here we've got a nice linear transform. Let me write down that from a coordinate perspective. I'm asserting that u bar I equals di x di. Remember, I'll do this peculiar dance. These are 4 vectors. J, we're going to sum over j. That's a bar, so that's a bar, and that's I. These two things here are the same formula. It's just written in a different notation, that's all. And I'm taking advantage of the fact that the Lorentz transform is linear. Actually, there's a slight infelicity of this, because we normally say letters I, J, K are summed or refer to 1, 2 and 3, whereas we take Greek letters summed over 0, 1, 2 and 3. We're including the 0 here if we use Greek letters. And I've kind of mixed my notation here, so I'm going to rewrite that just to make that plain. U bar alpha equals di x bar alpha by di x beta u beta, where u and u bar with components alpha and beta here are the 4 velocities. As measured in my reference frame, which is here, and Baz, who's moving relative to me, who uses Lorentz transformations. And this shows the utility of the four velocity approach, because we can just use matrix algebra to decide how the components change, and they're linear and everything works nicely. So that's really nice. I'm really rather, yeah, that's a good way. I'm going to stop there. That's nice. Stop.